Welcome to another episode of CUDA Education. Today we are just trying to finish up our series on adding new particles to our algorithm. Um, Previously we had you know we have our default application here, and all we're trying to do is basically add a new set of particles here um, that are moving around in its own pipeline. Okay, so we're trying to be as independent as possible from all that's going on here. We're setting up a new pipeline, we're adding new particles, and the particles are moving around. The reason why I make sure the particles are moving around is because it forces us to actually have to deal with compute related stuff. If we just had particles displaying here stationary, then all it would be a trivial matter of just adding particles to sort of the graphics part of the algorithm. But what we want to do is also go through the complexity of doing computation, random movement of the particles. Like all of these random movements it's being calculated. Um, it is being calculated on the compute side, right? So we try to make it as independent as possible. Now, obviously, it's not completely independent because I only have one GPU on my system. So regardless of what we do here, and regardless of how hard we try and make things independent with its own pipeline, its own storage buffer, its own everything, we still have to deal with the fact that and synchronize for the fact that we are we're only processing this stuff on one GPU, right? So that is the task at hand. And we have our algorithm here. On the left is the default algorithm. On the right is the changes that we've made in order to have these new set of particles and everything, right? So as you can see here, these are the changes that are made in order to in order to make in order to make the algorithm have the new particles. We have already done everything up to prepare corner particles, and now we're just trying to finish everything else. I am going to run the new particle system algorithm in this video. I'm trying to be done with it and just be done with it and not have to revisit this task any longer. So let's continue. So we're now in the prepare descriptor pool function, and basically previously we had uh, the descriptor pool size, we per frame we just had one. Here per frame we have two, and that makes sense because in the new algorithm we're dealing with a new set of descriptors, right? So in the descriptor pool info, the descriptor pool create info, we have two for the frames, and then for the new algorithm we have um, and the reason we have two here is because we have graphics plus compute, right? But over here we have graphics plus compute plus corner compute, right? Because we have now the corner particles that we have to deal with, right? So in the new set we have um, we have graphics plus compute plus the new compute, right? Um, so that's for the descriptor stuff. As we continue, this is pretty much the same. I really should update it so that it doesn't. Well, anyway, yeah, that's pretty much the same. And then down here, we call our new functions, which we've gone through before. In the prepare function, we call the new functions. We have to pay attention to where these changes are being made. So this is in the prepare function. We're calling our new functions. Um, in the build graphics a command buffer, we now have to bind the corner graphics pipeline, right? And notice that what we're using here is VK bind point graphics, right? So um, So notice that we're doing VK bind point graphics for this. If we look at the definition for uh, VKCMD bind pipeline, command buffer, pipeline bind point, and the pipeline. Okay, so we have the bind point graphics. This can change depending on what we're trying to do, and then of course we we bind this new corner pipeline. Okay, um, VK device size, and then we VKCMD bind vertex buffers. So um, this is related to our storage buffer stuff. If we look at the definitions for this, we have go to definition, command buffer, first binding, binding count, buffers and offsets. Command buffer, first binding, binding count, buffers and offset, right? So this is the buffer and that's the offset, okay? So that's that for the bind vertex buffers, right? And this is all under, we have to be aware of what function this is under. This is under build graphics command buffer. Okay, so this is all under the build graphics command buffer. Okay, and we're binding the pipeline, the graphics pipeline, corner graphics pipeline, for presentation and all that stuff, right? And then we got to be careful of what functions these changes are happening in. So submit corner compute, okay, independent. Now this is under the render function. So now we're actually we're in the render function, and we now have added processing for. So we have our regular submit compute commands, right? So that's that. But then we also have our corner compute. So remember guys, I said that we force ourselves to have to deal with computation for the corner particles, and we do that by making the particles have to move in the corner. Okay, so here we have submit corner compute, right? So now we have to interface. So we have a fence and we have a reset. So here we're building submit corner compute. So we have our fence to make sure that the previous work you know has been done before we attempt to re-record. We after we've done waiting, we reset the fence so that it could be signaled again, and then we build corner compute command buffer again. We re-record and we submit. Um, VKQ submit, and we have our associated fence. VKQ submit. Let us just actually go to let us go to that. VKQ submit. So we have our queue, our submit count, our submits, he submits, and the fence. So queue, submit count. This is just an info, right? This is just info. The SI is just info stuff. And then our fence to make sure that everything. So we have to make sure that this guy, we have to make sure that this guy, basically, make sure that we signal when we're done with this, that we signal this so that we could proceed again towards the next frame. So this submit corner compute is inside of the render function, right? If we look here, it's inside of the render function. Notice that the render function also makes sure that everything is prepared before we get to this. So we submit compute commands and then we submit corner compute commands, right? Um, and then notice that we have, so we're continuing on our path. This is still inside of render. So we're still inside of render. Okay, good. So we're still inside of render. Now notice that um, we now, instead of having two flags, we now have three flags. We have stage color attachment output bit VK vertex bit and then stage vertex input bit. So we have an extra flag for our extra corner particles processing, right? So we have an extra flag for the pipeline, for the pipeline barriers, pipeline synchronization stuff. Let us actually look at that. This doesn't really give us a definition, but so we have three semaphores. Let's look here. We have before we had 2 and 2, okay? Here we have 3 and 3 because we have an additional vertex input here, and then we also have an additional corner particles complete, right? So presents complete semaphore, compute semaphore, and then corner particles complete, right? So we've added another synchronization semaphore that we have to wait on, right? And then notice that wait semaphore count is 2 here, it's 3 here, okay? And that just makes sense with all that we're doing. Yeah, guys, I know this is rough around the edges, and it is also just a lot of code. But what I'm going to do is I'm going to actually run this new algorithm now, and you're going to see all that we have worked for. Okay, so let's run this new algorithm, and we'll see the fruits of our labor. So we could see here, guys, that we have the default application here. And then in the corner here, we have our new particles that are also moving around. Okay. Um, Again, it's a lot of work to get this stuff done. I know, I know. Again, Vulkan is very low level and verbose. So yeah, it's a lot of work, right? It's a lot of work. But once you get comfortable with why the rhyme and reason of why this stuff has to happen, it wouldn't be as intimidating. Now, I'm going to readily admit that, just off the top of my head, or like for most people, just off the top of their head, you're not going to be able to just generate this new code, you know, in 30 minutes, right? It's going to take time and stuff, but um, we can see that we have our independent particles here, different from what's here. They're trying not to get in each other's way as best as possible. Obviously, it's one GPU, so there is some synchronization and work that has to happen in order for that to happen. Notice that we have the particles are moving, um, and sort of even when these particles move over here, they're not, it's not necessarily getting in each other's way. This particle system is not necessarily aware of this particle system, and vice versa. So there's no physics consequences or anything. Um, you know, I know it's a lot, guys. Don't get intimidated. One day at a time. One day at a time. One day at a time. I did want to. I did want to play around with this. So first of all, um, so yeah, so let us now what we're doing here now is I promised that I would disable, so I will disable this guy and we'll see what happens. So if we simply disable this draw, now this draw call lives within inside of build graphics command buffer. So build graphics command buffer, and we're binding the corner graphics pipeline and all that stuff. So what we're going to do is we're going to simply comment out the draw call, right? We'll leave everything the same, but comment out the draw call. So when we do that, we basically get our original application. So for all the work that we've did, just because we comment out this draw call, we no longer have our particles because we're not drawing anything. It's that simple, right? Nothing crashes, either runtime or compile time. Nothing crashes. We just don't draw. So we do all this work and we don't draw. Obviously, we want to draw because we're a drawing group of people. Um, and then the other thing I wanted to do was where is it? Where is it? There was a number of particles. Right. It was the number of particles, right? So if we go up here, right? So if we just have 10 particles, we'll basically see that we just have our 10 particles, okay? One, two, four, three, 6, 10, right? So we have our 10 particles, right? And even if we go to 0, I believe my application won't crash, but we shall see. We shall see. It crashes. No, it crashes. Okay. All right. So we need at least one particle. We're not gonna get into why that is, but yeah, we need at least one particle. Okay. So we got one particle there. All right. It's like Pac-Man. You guys know? No, not Pac-Man. Ping pong. Back in the days, in the Atari days, there was like one thing going across the screen. We've come a long way, guys. Anyway, and then we could do 1,000 particles, right? And if we do 1,000 particles, we might not even have enough space to show everything. It would just be like one big blob, right? So there's 1,000 particles for you guys. Okay. Um, and we could do. Maybe it's too many particles. I don't know. Um, are you guys still recording? Yeah, we're still recording. So now we just have a paste, guys. That's interesting. All right, so let's just do 10,000. All right, so we still have whatever, but you guys get understand the drift now, right? Um, but yeah, guys. The reason why I exist and why we do what we do is to basically learn, right? So we're gonna learn. I'm gonna carry you through all of the crazy. I'm not gonna pretend like I know everything, but we're gonna learn Vulkan as we go, right? This is a long-term process, and this is why I say, guys, don't waste 2026. Start the process of learning Vulkan. You could start with what I'm doing here, and then move on to other other resources online. Now, they just had the 2026 Vulcanized conference, and that was very, very useful and interesting information. You could look it up on YouTube. Just look Vulcanized 2026, and you will see all the discussions and all the things. It's all on YouTube, and you'll be able to see all the wonderful things that people are working on, and all the issues, and all the big players in the industry and stuff. So anyway, guys, this is CUDA Education. This is if you want to be able to run this stuff and get all these examples, you need tutorial number one that installs the Vulkan SDK, and then tutorial number 13, which installs all of these examples. I assume you have a Windows-based machine with a Vulkan-capable GPU. If you want to be able to run the if you want to be able to run the ray tracing stuff, you have to make sure your GPU is also ray tracing capable. Um, you don't necessarily need an integrated graphics card. A dedicated discrete graphics card. You might be able to run if you bought a fairly new um, computer in 2026, you might be able to run just on the integrated graphics card. So make sure you do your research on what the capabilities are of the graphics card that you're going to be purchasing, or the computer that you're going to be purchasing, and what the capabilities of the graphics card is, so that you will be able to run Vulkan. Okay. The older integrated graphics card doesn't run Vulkan by or isn't able to run Vulkan by default. Anyway, guys, we're done with this, and I'm kind of happy that we're done. A lot of changes, guys, a lot of changes in order to get the particle system going. But again, we're here to learn. We are here to learn. So that's it. Have a great day. Goodbye.